Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. In networking, not all addresses are manually assigned or obtained from centralized servers. Sometimes devices need to assign their own addresses, either due to failures in configuration systems or by design to support automated environments. These self-assigned address systems play a key role in keeping networks functional, even when services like DHCP are unavailable. They also support scalability by enabling hosts to configure themselves with minimal administrative overhead. In this episode, we'll explore two key auto-assignment methods, APIPA for IPv4 and EUI-64 for IPv6, both of which appear frequently in real networks and on the Network Plus exam. Auto-assigned addressing exists to provide either fallback connectivity or dynamic scalability. APIPA, short for Automatic Private IP Addressing, allows devices to self-assign an IP address when they cannot reach a DHCP server. It ensures that devices on the same local subnet can still communicate, even in the absence of centralized configuration services. EUI-64, by contrast, is used in IPv6 environments to automate interface identifier generation. It extends a device's hardware address into a routable IPv6 address, eliminating the need for per-device manual IP configuration. Together, these two technologies illustrate how networks remain resilient and self-sustaining even under adverse or large-scale conditions. APIPA is an IPv4 mechanism that assigns an address from the 169.254.00/16 block. This special range has been reserved by the Internet Assigned Numbers Authority specifically for local link self-assignment. When a Windows or other DHCP-manipulated device cannot obtain a lease from a DHCP server, it automatically selects an address from this block to maintain limited connectivity. This allows local file sharing, printer access, and other peer services to continue functioning on the same subnet even though access to the Internet or remote networks is not available. The process APIPA uses to assign an address begins with the host selecting a random IP within the 169.250.2410 to 169.250.24.254.25.5 range. It then sends an ARP request to the subnet to check if the address is already in use. If no other device responds, the address is deemed available and is assigned to the interface. If a conflict is detected, the device selects another address and repeats the process. This method ensures that no two devices on the same segment inadvertently use the same IP, even though there is no DHCP server coordinating assignment. Despite its utility, APIPA has significant limitations. Because it does not assign a default gateway, devices using APIPA can only communicate within the local subnet. This means there is no path to the Internet or any other routed networks. APIPA is designed for local fallback, not full network connectivity. As a result, it should be seen as a signal that something has gone wrong. Typically, DHCP has failed, and that corrective action may be necessary if external communication is required. There are several use cases for APIPA. It is commonly encountered in small or unmanaged networks, such as home peer-to-peer setups or classroom labs, where a DHCP server might not be present. It also serves as a temporary mechanism during network outages, helping users diagnose configuration issues. For example, a technician might notice that a workstation has self-assigned a 169.254.x.x address and immediately suspect DHCP misconfiguration or server failure. In these cases, APIPA helps maintain basic LAN functionality while signaling the need for further troubleshooting. When diagnosing connectivity issues, recognizing an APIPA address can quickly guide your next steps. If a user reports they cannot access the Internet and their computer has a 169.254.x.x IP, this strongly suggests a DHCP issue. Tools like ipconfig on Windows or ifconfig on Unix-like systems can display the currently assigned IP address, making it easy to identify when APIP is active. The operating system may also display a message such as limited or no connectivity, reinforcing the presence of a fallback address rather than a full network assignment. EUI-64, which stands for Extended Unique Identifier, is used in IPv6 to generate a host interface identifier automatically. Unlike IPv4, which often requires manual or DHCP-based assignment, IPv6 is designed to support self-configuration at scale. EUI-64 achieves this by using a device's MAC address to generate the lower 64 bits of the IPv6 address. This address is then combined with a 64-bit network prefix, which is typically provided by a router advertisement, to form a complete 188-bit IPv6 address. The EUI-64 format converts the 48-bit MAC address into a 64-bit interface identifier. To do this, it splits the MAC address into two 24-bit halves and inserts FFFE in the middle. For example, a MAC address of 01A to B3C4D would become 21A to B FE3C4D5E in EUI-64 format. In addition to inserting FFEF, the 7th bit in the first byte is flipped to indicate that the address is globally unique or locally administered. This bit flip differentiates an EUI-64 identifier from its source MAC, while preserving uniqueness and compatibility. Using EUI-64 has some privacy implications. Because the generated IPv6 address is based on a hardware identifier, it remains consistent across networks unless manually overridden. This can allow tracking of a device as it moves between networks, raising privacy concerns for users. To mitigate this, many modern operating systems implement privacy extensions that generate random interface identifiers that change periodically. These temporary addresses can be used for outbound connections, reducing the exposure of the device's hardware identity. EUI-64 can be used in both dynamic and static configurations. In dynamic environments, EUI-64 is used with stateless address auto-configuration, SLAC, allowing devices to create their own IP addresses without the need for DHCP-v6. In static environments, administrators may manually specify an EUI-64 address or disable it in favor of fixed assignments. Some systems allow toggling EUI-64 behavior or disabling it entirely, depending on the needs of the organization or the level of privacy required. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Stateless address auto-configuration, often abbreviated as SLAC, is one of the primary ways IPv6 hosts use EUI-64 to build their own addresses. In a typical SLAC scenario, an IPv6-enabled router sends periodic router advertisement messages that contain the network prefix and relevant flags. Upon receiving this prefix, a host uses EUI-64 to generate the interface identifier portion of its address, combining the two into a full IPv6 address. This process requires no DHCP server and no manual configuration, making it highly scalable and resilient in dynamic or large-scale environments like IoT networks or corporate campus LANs. Comparing APIPA and EUI-64 highlights the similarities and differences between IPv4 and IPv6 self-assigned addressing behaviors. Both allow devices to self-configure in the absence of traditional configuration methods. APIPA provides a temporary local-only IPv4 address when a DHCP server is unavailable. EUI-64, on the other hand, is a method for creating a routable IPv6 interface identifier by extending a MAC address. While APIPA only allows limited LAN communication, EUI-64 supports globally routable addressing when paired with a proper IPv6 prefix. Functionally, APIPA is a fallback, whereas EUI-64 is part of the design of scalable IPv6 networks. Security is a major concern with self-assigned addressing, particularly with EUI-64. Because the address is derived from a device's MAC address, it remains constant across networks unless actively masked. This makes it easier for adversaries to track a device's presence or movement over time. For example, if a laptop connects to different wireless networks but keeps the same EUI-64 address, that identifier can be used to build a profile of the user's activity. To counteract this, modern operating systems include features like IPv6 temporary addresses, which use randomized interface identifiers that change periodically reducing the ability to track users. Administrators can disable or override APIPA in environments where unmanaged fallback behavior is not desirable. On Windows systems, for example, APIPA can be disabled through the registry, while Linux and Mac OS offer configuration files or commands to prevent its activation. This is often done in tightly controlled enterprise networks where fallback addressing can mask more serious problems, such as DHCP server outages. Preventing APIPA forces the system to remain offline until it obtains a valid address, drawing attention to configuration failures that need to be addressed by IT staff. In the case of EUI-64, the router plays a central role in enabling the address construction process. Through periodic router advertisements, the router supplies the prefixed portion of the IPv6 address, typically the first 64 bits. The host listens for these advertisements and then appends its own interface identifier, generated using EUI-64, to form the complete address. If the router does not send advertisements, or if the prefix is not marked for auto-configuration, the host cannot generate an address using this method. Routers must be properly configured to support SLAC and may also advertise other information such as DNS server addresses. Vendor-specific behaviors can influence how EUI-64 is implemented across different systems. For instance, some operating systems use privacy extensions by default, generating temporary IPv6 addresses instead of using EUI-64. Others may prioritize DHCP v6 over SLAC, especially in enterprise environments where address management needs to be centralized. In some cases, hosts may have multiple IPv6 addresses, one based on EUI-64, one randomized, and one assigned by DHCP v6, each used for different types of communication. This variation highlights the importance of understanding the local IPv6 stack and configuring devices to meet the organization's operational and privacy requirements. On the Network Plus exam, expect to see questions that ask you to identify auto-assigned addresses by their characteristics. You may be presented with a scenario in which a device has an IP address in the 169.254.00/16 range and be asked what that indicates. You'll need to recognize this as a APIPA and deduce that a DHCP failure has occurred. Similarly, if shown an IPv6 address with a suffix that includes the hexadecimal value FFFE in the middle and a flipped 7th bit, you should identify it as an EUI-64 dejuggled address. These identification skills are critical for selecting correct answers and troubleshooting exam scenarios. Common exam scenarios involving APIPA might ask you to interpret why a workstation can print to a local printer but cannot access the internet. Identifying that the workstation is using an APIPA address helps you conclude that DHCP is unavailable and the system is operating on a fallback mechanism. EUI-64 scenarios often appear in the context of IPv6 SLAC, where you'll need to explain how a device formed its address or why it lacks one. Understanding how these automatic systems function and when they are appropriate or problematic is a key part of network-level knowledge. In conclusion, APIPA and EUI-64 are both examples of how networking protocols enable devices to self-configure, maintaining basic functionality even when centralized services are unavailable. APIPA supports IPv4 networks with fallback addressing limited to the local subnet. EUI-64, in contrast, is a mechanism used in IPv6 to support large-scale auto-configuration by generating globally unique interface identifiers. Both have security, privacy, and design implications that must be considered. Whether you're diagnosing DHCP failures, building scalable IPv6 networks, or preparing for certification, a strong understanding of these auto-addressing methods ensures reliable, secure connectivity across varied environments. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, Make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.